Okay, right now I'd like to introduce today's presenters. Stefan Hopfe is a product manager of thermal interface materials at Semikron. Stefan joined Semikron in 2011 as a product manager, and since 2013, he solely focuses on the technical assessment, strategy, and implementation of thermal interface materials into the complete product range of power modules in Semikron. Now also joining us today is Stefan Hauser. He's a Senior Manager of Product Marketing International at Semikron. Joining Semikron in 2011 as a product manager, he changed to his current position as the Senior Manager for Senior Product Marketing for the complete range of power modules in 2015. Now, beside the IGBT and thyristor and diode-based power module market, he also focuses on silicon carbide power module strategy. So, gentlemen, welcome to today's event, and with that, I'm going to pass things along to Stefan Hauser to get us started. So go right ahead.
Let's have a look to the agenda first. First of all, I'm going to give you a short company overview, who is actually Semikron. After that, we are going to deep dive into thermal interface materials. Why do we need them? How do they work? And what materials are available in general and at Semikron? Then we're going to talk about how to optimize the thermal interface layer and what is the benefit of this optimization. And finally, before we conclude, we are going to talk about pre-applied thermal interface material and what that can do for you in your application. Let's start with a company overview. Semikron has its headquarters in Nuremberg, Germany. We are a privately owned company founded in 1951 by Dr. Fritz Martin. We have about 25 operating companies worldwide. 9 of those are not only sales offices, but actually production site for our various products. We have approximately 3,200 employees right now. 1,700 of those are working in our headquarters in Nuremberg. There we have roughly 42,000 square meters of company grounds, and the turnover in 2018 was 528 million. Semikron is one of the biggest independent power electronics manufacturers worldwide. Independent here means that we have the free choice of IGBT and MOSFET chip to really optimize our products for certain markets, for certain applications. Our portfolio ranges from chip to system with all intermediate steps of vertical integration. We have a chip fab here in Nuremberg where we produce our rectifiers and thyristors and also our freewheeling diodes. These we combine with IGBTs or MOSFETs into our power modules. Today we can say that we have all industry standard power modules available in our portfolio for serving all kinds of applications. For high power wind, solar traction applications, we specifically offer our IPM, our intelligent power modules. Here they are called intelligent because we add a driver, sensing functions such as temperature sensor, sensing for the current, for the DC bus voltage, as well as protection functions, and mount these on heat sinks which can be either water or air cooled. The next level of integration are the power electronic stacks, where we also include a DC bus and a housing and build a ready-to-use assembly. So here the customer only has to connect a controller to create his own system. If you're looking for complete inverter system, we also offer that, but here also specifically for a market, for automotive markets. We have 2 different versions. We have a low voltage inverter system for battery vehicles such as forklifts or mild hybrid vehicles, and we also offer high voltage systems for example, electrified trucks and buses. So far for the introduction, and now I would like to hand over to my colleague Stefan Hopfe for all the details on thermal interface material.
Okay, thank you very much, Stefan. Now I will come directly to my first point and the question, why do we need thermal interface materials in principle? When we have a look to an assembly of a module mounted on a heatsink, there are different layers. starting with the heat generating chip. The chip is soldered on a substrate, the substrate soldered on a base plate, and the base plate mounted on a heatsink. And the heat flow coming from the chip needs to pass all these layers. And between the power module and the heatsink, there will be the thermal interface material. And when you have a close look to such a surface, you can imagine the surface will not be very even. There are small gaps between module and the heatsink, and air is a very bad thermal conductor, means I need to fill out these air gaps with a better thermal conductive material. Then the working principle of thermal interface materials. So what is for all thermal compounds mostly the same, they consist on a carrier material and a filling material. The carrier material is responsible for the wettability and the flowability of the compound. And this can be any kind of silicon base or silicon free oil or any other synthetic fluid. And this ensures the easily distribution of the material between the power module and the heatsink. Then you have the filling material. The filling material is responsible for the heat transfer. Here are mostly metal or metal oxides used, for example aluminium or zinc oxide or bore nitride. You have different particles at different shapes or size, and the ones with the low thermal resistance are preferred. Okay, then some more explanation about the particles and the particle sizes. When we have a look again to the assembly with the mounted base plate on the heatsink, you can see where the module directly touches the heatsink. You will have the best heat flow. Then, when I put in the compound only very large particles, this has two disadvantages. The first one is you would increase the gap between the base plate and the heatsink and make a metal-to-metal contact completely impossible. The second point is large particles are not able to touch the surface, to contact the surface properly. So somebody could say, okay, so I put in the compound only very small particles, but also this is not an optimum. When you see in the middle, where you have a lot of small particles, the heat flow will be very small. And why? Because between each particle I have another thermal resistance. Each interconnection means I have an additional thermal resistance. So at the end the heat flow will also very bad here. So the consequence is I need an optimum particle size and particle distribution for a good compound. Then a last point for the working principles, the filling degree. The filling degree plays a major role for the performance of the compound. So when I have a look to the left box, I can see a filling degree of 60%. And even I put in very high thermal conductive fillers, the overall performance of the compound is still very bad. So how to increase the performance? I put in additional smaller particles and increase my filling degree to almost 80%, for example, what you can see on the right. So the performance of the compound is now much better. So in principle we can say the overall performance of the tin material in an assembly is always a function of the thermal conductivity of the filler, the particle size, the particle distribution, the filling degree as mentioned now, and also the thickness between the power module and the heatsink, and also power module specific parameters like the pressure which is coming from the module. Please remember these parameters. I will show you later in the presentation how these can be optimized. Then the thermal interface material options. Okay, so now have a look to which kind of materials are available on the market. On the one side we have the paste systems like a common thermal crease. These are mostly based on silicon or silicon-free fluids and filled with metal or metal oxide particles. On the other side, we have solid systems like thermal pads or foils. For example, here we have one-layer systems like a graphite or indium sheet, or multi-layer systems like aluminium base with a phase change layer on top and bottom. And between both, we have the transition systems like phase change material. Phase change materials are typically solid or rigid at room temperature and getting viscous or pasty at temperatures above 45 degrees. Also these are filled with metal or metal oxide particles. And when you now have a look to the right picture with the light blue bar, what is showing the thermal pad here, you can imagine that a pad is mostly or rarely not as good as a paste or a transition system to contact the surface properly. Then, which kind of materials do we have here at Semikron? So first of all, since a lot of years, we have a standard thermal crease which is silicon based and zinc oxide filled and has a thermal conductivity of 0.8 watt per meter in Kelvin. The compound can handle operation temperatures of up to 200 degrees. Then some years ago we introduced our high performance thermal paste, which is also silicon containing and zinc oxide filled, but has a datasheet value of 2.5 watt per meter in Kelvin. And also this compound can handle operation temperatures of up to 200 degrees. Then, mainly for our baseplate modules, we offer phase change materials. In principle, we have two options. We have one for higher performance and another for higher temperatures. Both compounds are filled with wax and contain aluminium particles. The high performance option has a thermal conductivity of 3.4 watt per meter in Kelvin, and the maximum heatsink temperature which is allowed is 105 degrees. Then when higher temperatures are requested, you should choose the other option, which is additionally filled with zinc oxide particles and has a thermal conductivity of 3.0 watt per meter in Kelvin. But this compound can handle operation temperatures on a cooler of up to 125 degrees. Then, in the next step, I want to lose some words about how to optimize the performance of an existing thermal interface material. So I would place now the question in, why is it that important to have a close look into thermal interface materials? When you remember to the assembly of a module, in the overall path from the chip to the heatsink, the thermal interface materials represent the biggest share of the overall thermal resistance. So the TIM material is taking around 50% for a baseplate-less module in the overall thermal resistance. That's why the advantage here is the highest to make any improvement in this layer. You can drastically reduce your thermal resistance and increase your power density and the output power and the lifetime of your module. The first step in this optimization would be to choose the right material for your power module and your application. When you remember particle size, particle distribution, filling degree, thermal conductance of the filler, these are parameters guiding the compound, guiding the performance of the compound. And the Semikron answer for an absolutely optimized compound has the name high performance thermal paste. I will give an example here. I take a mini-skip half-bridge module 1200 volt 200 amp. This is set standard for low or medium power motor drives. It's an industrial standard baseplate-less power module with spring technology and an easy PCB mounting concept. The module is scalable from 1 to 90 kilowatts. When I take this module and I place a standard grease there, this would be my reference in the thermal resistance junction to heatsink of 100%. When I now replace the grease and place a high performance thermal paste here, then I gain an advantage in the thermal resistance by up to 50%. And what does it mean? With a benefit in the thermal resistance of 50%, I can increase the output power of one and the same module by up to 25%. To increase the output power and the power density of the module is just one option. Another one would be to significantly reduce the operation junction temperatures. And a reduction of the chip temperatures would mean a longer module and inverter lifetime. Let's have a look to the graph over here. The x-axis describes the output power, the y-axis the operation junction temperatures. And as mentioned, I can increase the output power by up to 25%, or I can lower the operation temperatures by up to 33 Kelvin. And of course, a combination of both, more output power and longer lifetime, is possible and can be seen as a trade-off. So each point on the blue line is a combination of both. Chip temperature reduction is therefore more lifetime of the module and more output power. So coming to the second step of the optimization, the layer thickness. When we have a look to the left picture, we can see that much too little TIM material is applied on the surface between the power module and the heatsink. Means we leave very large air gaps here. When we have a look in the graph above, we can see that the thermal resistance is increasing dramatically. When we have a look to the right picture, we can see that too much material is applied on the surface. And this means also that the power module is not able to touch the heatsink and not able to establish any metal-to-metal contact. And in the graph this means the thermal resistance increases slightly over the thickness. And then in the middle we can see the picture for an optimum layer thickness between power module and heatsink. The power module partially touches the heatsink and just the roughness is filled out with the thermal conductive material. Here the thermal resistance is optimum, and this you can see in the graph as the green area. And the next slide shows some example of different layer thicknesses which has been applied on the power module. But before evaluation of any imprint pattern, we need to consider that the paste needs time to distribute after the module has been mounted to the heatsink. That's why we recommend to perform 3 or more thermal cycles to force the distribution of the grease. And then after the disassembly, we can have a look to the imprint pattern. The left one shows the example where too little grease is applied, and we have very large air gaps which significantly increases my thermal resistance. The right one shows the picture where shows the example where too much grease is applied. Here the thermal resistance is increased slightly. We have a clustering on the surface and the TIM material will be squeezed out on the edges. And besides these facts, we have also an increased risk of mechanical crack of the substrate, as the paste thickness is too high here. And the optimum is the one in the middle. We can partially see that we have metal-metal contacts, and we have no clustering here in the middle, and the thermal resistance is optimum. Then the application and the print pattern. For low-end performance, the application by roller can be sufficient, especially for the baseplate modules. But for high repeatability and for mass production, we strongly recommend an automated printing process in a clean environment. That's why Semikron uses a screen and stencil printing process in a clean room, and we apply a honeycomb structure on our power modules. The right picture shows the example for stencil printing, and the one in the middle for screen printing, and which method is used depends on the module assembly. And the fact that we apply a honeycomb structure instead of an even layer has two advantages. The first one is that the thin material easily distributes in the moment where the module is mounted to the heatsink. So in this moment, when the module surface with the thin layer touches the heatsink, exceeding air can easily flow out through the channels of the honeycombs. And the second point is that we have a very easy and convenient calculation of the resulting thermal interface material layer. Then, after explaining a honeycomb shape working principle in general, I also want to discuss a print pattern. In the past, it was mostly sufficient to apply an homogeneous honeycomb pattern for standard creases on our baseplate-less modules like the miniskip. But with the introduction of new higher viscous materials like the high-performance thermal paste, the need was given to apply also an inhomogeneous one. Let's have a look on the picture on the right. The red dotted line shows the pressure areas of this module. So around the housing and around the screw holes, the module will be pushed down to the heatsink. On these areas, the paste will be squeezed away anyway. That's why we apply less materials here. The target is to reduce the stress, the mechanical stress during assembly. For our baseplate modules, we go completely another way. Here we start to get a 3D surface scan on the copper baseplate. And our target here is to apply, especially on the screw holes, no tin material, as we have the best thermal contact without any thermal interface materials here. And we just want to fill out the cavities of the copper baseplate. That's why you can see in the middle more material is applied. So that's it from my side. Now I would hand back over to my colleague Stefan Häuser. Thank you.
Thank you very much for these great details about thermal interface material, Stefan. Now let's have a look into pre-applied thermal interface material and how that can help you in your application. So what does pre-applied thermal interface material actually mean? A pre-applied thermal interface material means that you purchase a power module that is already pre-printed with the thermal interface layer. For you as a benefit, that means you avoid an additional, actually quite dirty process in your own production. The modules that you purchase can directly be mounted. There's no additional treatment required beforehand. You have a great selection of thermal interface materials available to choose from. This selection is growing. Whenever we find a new material that looks interesting on the data sheet, we will do an evaluation. And furthermore, we will not only evaluate but also optimize to the power module. So this work, optimizing and printing, is relieved and outsourced basically to the power module manufacturer. Additionally, you also have a fully qualified product then, because also we are putting effort into qualifying not only the module but also the combination of the power module with the TIM layer. So you save a lot of work that you have to do around a material that in the end costs only a few 10 cents, but a lot of effort is necessary to make sure that it works optimized in your application. So now the question has to be asked, which thermal interface material on which type of power module? And here Semikron has a very simple guideline. We distinguish between baseplate-less power modules and baseplate power modules. For the baseplate-less modules, we clearly recommend go for a thermal paste. There we have the standard thermal paste, which is used today really in a lot of designs. It's well known, it's trusted, but limited in performance, but it's the one that you also will get from our competitors. The high performance thermal paste is a step beyond that. So here we have the highest output power because the thermal resistance is really optimized, really lowered, and this has to be the recommendation and the benchmark for new designs. On the baseplate power modules, we usually recommend go for the phase changer. Here you have the benefit that you cannot damage the print when handling, when mounting the module, but of course you compromise a bit on the performance. So with a high performance thermal paste on a baseplate module, you will always get a better performance than with a phase changer. So you really have to trade off here. Nevertheless, we have these two different phase change materials. The one that gives you a lower thermal resistance but is limited in temperature that it can be operated at. And the second one, the high temperature version, where you can really boost also the heatsink temperature to maximum 120 to 25 degrees, basically necessary for applications where you have not sufficient cooling, limited cooling, or just a convection cooler, not a forced air cooler. Now the question is, what products are actually available with thermal paste? Let's first have a look to baseplate-less modules. Here we have the standard and the high performance thermal paste. In the top row you see the semi-top with two generations, the semi-top 2, 3 and 4, which we refer to as the first generation, and the semi-top E1, E2, the second generation semi-top, which we also call an industry standard power module. In this case, industry standard means the same product with the same fit form function is also available from other manufacturers. The benefit of both modules is actually very high customization capability. Thanks to the flexible placement of the pins, a lot of different topologies can be fit into these power modules for all different kind of applications, motor drives, solar, UPS, just to name a few. We also have available the mini skip, which is the power module for the low and medium power range in motor drives. Has been in the market for more than 20 years, based on a spring design, which is a very unique concept for mounting and dismounting the module. So the mounting process is very fast with 1 or 2 screws. Basically you mount the PCB on top of the module, you mount everything together on the heatsink. So that is done very fast and is therefore perfectly designed for high volume productions. Available topologies are the standard topologies in motor drives. So you have converter, inverter, brake power modules where you have a rectifier, a brake chopper and an inverter stage combined in one power module. You have 6 packs, you have rectifier with our own chips as mentioned in the beginning. And this makes it the perfect scalable motor drive platform from 1 to 90 kilowatt. On the right hand side, on the bottom, you see the SCIM 6393. This is actually the power module with the thinnest thermal interface material layer that we are able to do. So here we find only 20 micrometers of thermal interface material. The module is very unique. It's a 6-pack power module. So a complete inverter, and it is completely solderless. So this was the first power module in mass production on the market coming with a sintered chip. All connections, if it's the power or the auxiliary connections, are done with a certain spring, respectively bus bar systems, which makes it the first solderless module on the market. Target applications here clearly are high reliability applications such as automotive or very high reliability, high performance power supplies. So much for the modules available with thermal paste. And now let's have a look into the products available with a phase changer. So these are mainly the base plate products as mentioned before. First of all, we have here the Semix series, which is a 34mm high series. available in half bridges, in rectifiers, buck boost converters, even in 6-packs if you look at the Semix 33C. We have the Semix 5, which is, thanks to its 5 terminals, actually perfect for multi-level applications, in this case 3-level applications with NPC and TNPC topologies, as well as 6-packs. So here we cover the complete markets of solar, of drives, of UPS, thanks to the flexibility in the topologies that we can fit in. Very traditional modules, 34 and 62 millimeter wide, are the Semitrans 2 and the Semitrans 3.4, but still very much used in the industry, and that also for a good reason. They are robust, they are well known, and thanks to our internal design, we also come with a very good switching performance because we have very low commutation inductances in the module. For the high power applications, we have the Semitrans 10. This one is available as a half bridge, as buck boost converters, but also in a specific multi-level topology called the split MLI, tackling solar as well as wind power applications. Also rectifier module, we have the Semipack 2 available now with a phase changer. Here this is a good example of the vertical integration as well, because in this rectifier module we use our own chips from Nuremberg. And with this module we create phase legs for rectifiers, uncontrolled, half-controlled, as well as full-controlled if we place the thyristors. And the big exception, as you see on the bottom right corner, this is the Semitop E1 E2, which we already had on the slide before for the thermal paste. So this is the only baseplate-less module that we also provide with phase changer. Why do we do that? Well, first of all, the market requires it. We talk here about a press fit module, so you have to press in the module into a PCB, and that of course is a little bit easier if you cannot destroy the honeycomb structure so easily as you would do with the thermal paste. This gives the nice advantage, but you also have a disadvantage, right? So the disadvantage here is the performance. If you compare the phase changer against our standard thermal paste that we use as a design standard or as a reference here, then we have a 10% reduced RTH. If we compare the HPTP, the high performance thermal paste, to the standard on that module, then we have a 40% reduced RTH thermal resistance. That means if you want the easiest handling, again, you go with a phase changer. If you want the highest performance, you should use the high performance thermal paste. I mentioned before that the customer buys a qualified product pre-applied with TIM. But that means we also have to qualify actually the TIM layer printed on our module. And this is what we do in a two-step qualification process. So first of all, we have to validate the shelf life of the pre-printed module. That means we have a 12 to 18 months shelf life. That's depending on the used material under certain conditions, where we have to make sure that the thermal resistance does not increase too much over time. And in order to validate that, we do several tests. These include high and low temperature storage tests. So we store the module at a certain time at a very high, at a very low temperature. We do some thermal cycling, and we also do climatic change test. So vary the temperature and the relative humidity at the same time. After that, we mount the module, and we expect to be the thermal resistance maximum 20% higher than on a measurement that we do on a reference module without seeing all these tests. In the second step, we also have to validate the mounted module in the application. So additional to the power module qualification, we of course do a thermal resistance reference measurement. We do power cycling, where we really simulate a high power usage of the power module. We supply damp heat. We do high and low temperature storage, and that all mounted on a heatsink. And here again, we compare after all these tests the thermal resistance, and we expect or allow only a 20% increased thermal resistance compared to the reference measurement. In order to receive a high-quality thermal interface material print, it is also important to have a good look on the production environment where you do the print. In our case, we have a dedicated clean room environment where the printing is done. That is an ISO 6 clean room. And the TIM print is made to order. So when we stock power modules, these power modules are always unprinted, naked. And the moment that we receive an order for a power module including a thermal interface material, the print is done. Benefit is that the shelf life is not compromised and you get the benefit of the complete shelf life time. Our printing process is fully automated. We have, of course, some manual handling before and after, but the printing process is fully automated, giving the highest repeatability in the process. We also include a statistical process control, and what we do is we measure the weight of the module before and after printing, and the difference gives us an indication of how thick the layer finally will be when it is mounted in your application. Beside that, there are several optical control steps included, as you can see on the lower hand picture. Now it's time to conclude this webinar. We have shown you today in this webinar that it is absolutely crucial to the complete system performance to optimize the thermal interface material layer. This gives the biggest leverage in terms of thermal performance in a given system. Whether you want to optimize or maximize the power density or minimize the operation temperature, that doesn't matter. The key is the thermal interface material. This means the choice of the material, the layer thickness and the print pattern has to be optimized, and this can lead to an improvement of the thermal resistance by as much as 50%. By going for a pre-applied thermal interface material on the power module, you save additional production steps, and with this you also make sure that you receive a product that is high quality printed and fully qualified, not only the module but also the thermal interface material layer. And finally, you gain advantage of Semikron's almost 30 years experience and more than 15 million modules with pre-applied thermal interface material running today in the field. Thank you very much for your attention.
Okay, gentlemen, thank you for that presentation. Now let's go ahead and take a look at some questions that have come in from our audience today. Our first question asks, is the improvement of HPTP compared to the standard thermal paste the same for all modules?
No, not at all. The improvement strongly depends on which module assembly I have. So there's a difference between baseplate or baseplate less module. And it also depends on the chip layout or chip size. There's a difference between large and small chips. So in general, you can say the larger the chip area is, the higher my improvement will be. And why? A large chip causes a large bending in the substrate due to the solder process and a large TIM thickness below the substrate. So the more I depend on the performance of the TIM material.
Okay, great. Thank you. Our next question asks, what about silicone-free thermal interface materials? Do you have these available too, or do you plan to have them?
But I think you talk about the creases. So we had a silicon-free version in the past, but we discontinued it because it is mostly worse in behavior and reliability compared to a silicon-based grease. We had a very low demand, and this is the main point. We had the evidence that the silicon inside the compound is no risk in an automotive sensitive area, which was shown in a test according to VW standards. Yeah, and by the way, the module itself contains also a lot of silicon as the soft mold, and it would not make sense to strictly ban it as a TIM material.
Okay, thank you. Next question is, do you recommend to run in a phase change material, i.e. they're stating a heat up the complete assembly before the first time full power is run.
Yes, that's a frequently asked question from customers, and also doubts are plausible here. But our overall target was to keep the use of our modules with pre-applied phase change material as simple as possible. Means we want to avoid the requirement from any burn-in process, and we also want the requirement of a retightening process of the mounting screws after the first time run. So in consequence, we created a print pattern according to these requirements for each module type separately. And what ensures that we have a very good thermal contact from the very beginning on, and a very good thermal resistance. And the module don't need to be retightened at any time. So yes, the module can be fully loaded from the beginning on.
Okay, thank you. Next question here asks, can you tell me about degradation of the thermal interface material over time?
In general, all compounds are subjected to an aging process driven by high temperature and humidity. What mainly happens there is that the binding force between the matrix and the filling material is getting lost. Means the oil and the filler separates and the oil is flowing out. And this is so-called the blood out of the paste. And very often the consequence in the application is we have a gradual increase of the chip temperature over the lifetime. And this increase again accelerates the aging process of the TIM material because the module is getting more and more hot.
Okay, and one more question for you. Can you relate from the datasheet value for the thermal conductivity to the overall thermal performance?
No, not at all. Or not necessarily, let me say. Even a TIM material has an outstanding thermal conductivity to thermal performance under the module can also be very bad. Why? We have two possible reasons here. The material could not be able to contact the surface properly because it is too stiff or has too large particles inside, or the gap width is too large, means the TIM material is too thick and not able to be pressed down below thicknesses of less than 10 microns, what is our requirement for the modules. And this is mostly specified as the bond line thickness.
Okay, great, Stefan. And with that, we're going to wrap this webinar up right there. We'd like to thank everyone for joining the Semikron webinar to learn how thermal interface materials work, how to choose the right material, and how you can benefit from pre-applied materials in your application. Take care, everyone, and have a great rest of your day.